There are speed limits in the universe, not just for light, but for growth, for creation itself. A star, a galaxy, a living thing. Everything is bound by the tyranny of time, by the patient metered accumulation of matter and energy. Nature, it seems, has rules against getting too big too fast, and yet in the deepest chasms of cosmic time in an era so remote we can barely comprehend its existence, we have found monsters. Monsters that break the rules. Celestial phantoms of impossible size born in a time of cosmic infancy that stare back at us across 13 billion years of expanding space and ask a terrifyingly simple question: how? To find the answer, we must leave everything we know behind. Not just our world or our solar system or even our galaxy, but our entire conception of a mature, orderly universe. We must travel backwards. Far beyond the familiar spiral arms of the Milky Way past the neighbouring glow of Andromeda, our sister galaxy, a destination that even at the speed of light would take 2.5 million years to reach. We push further, accelerating our journey through the intergalactic void, watching as entire clusters of galaxies, these glittering cosmic cities, blur into faint smudges of light, then vanish from view. We fly through the Hubble Deep Field, a region of sky once thought empty, now revealed to be a tapestry woven with the light of 10,000 ancient galaxies, each one a universe of its own, with its own history, its own destiny. But our destination lies deeper still. We are pushing beyond the reach of even our most powerful optical telescopes, beyond the last of the great structured galaxies. The universe grows younger, hotter, and stranger with every light year we cross. The familiar cosmic web, that vast, intricate scaffolding of dark matter, along which galaxies are strung like pearls, begins to dissolve. Its grand architecture has not yet been built. The stars themselves begin to thin out their light, becoming redder, more stretched, a final mournful sigh from an age that is passing into memory. And then we plunge into darkness. A profound primordial blackness, punctuated not by the familiar glow of a billion stars, but by an oppressive uniform twilight. We have arrived at the edge of everything. Welcome to the cosmic dawn. We are now just 400 million years after the Big Bang. This number is so immense it feels meaningless, yet in cosmic terms it is nothing. If the entire 13.8 billion year history of the universe were a single calendar year, we would be in the first week of January. The Earth would not form until early September. Humanity would appear in the last few seconds before midnight on New Year's Eve. This is the nursery of the cosmos, but it is a dark and violent place. There are no grand spiral galaxies here, no elegant elliptical ones. There is only a pervasive universe-spanning fog of neutral hydrogen gas, a relic of the Big Bang's initial fireball, now cooled and coalesced into a murky soup. Within this fog, gravity is waging its first great war. Invisible filaments of dark matter, the universe's hidden skeleton, are patiently pulling this primordial gas into ever denser knots and sheets. In the cores of these nascent clouds, the pressure and temperature are climbing, building towards a critical threshold, a moment of cosmic alchemy. And here and there, like the first spark struck in an infinite cave, the very first stars are beginning to ignite. But these are not stars like our sun. These are behemoths forged from pure hydrogen and helium, untainted by the heavier elements that would come later. They are hundreds of times more massive, millions of times brighter, and they live for only a fleeting moment, burning with a furious blue-white intensity before exploding in supernovae of unimaginable power. They are the celestial blowtorches that will begin to burn away the hydrogen fog, carving the first bubbles of transparency into the cosmic dark. This epoch, this transition from absolute darkness to the first light, is where our story begins, because it is here, hiding in this primordial murk, that the mystery is born. According to everything we thought we knew, this infant universe should only be capable of creating infant things, small stars, small galaxies, and crucially small black holes. Our established model for how black holes form is elegant and tested. When a massive star, many times heavier than our Sun, exhausts its nuclear fuel, its core collapses under its own immense gravity. The collapse is so catastrophic, so absolute, that it crushes matter down to a point of infinite density, a singularity. This stellar mass black hole, perhaps 10 or 20 times the mass of the Sun, is the standard seed of darkness. From this seed, a giant can grow. But it needs food, and it needs time. Endless, unimaginable stretches of time. A black hole grows through a process called accretion. It is not a cosmic vacuum cleaner, but a gravitational anchor. Gas and dust and unfortunate stars that wander too close are ensnared in its gravitational field, forming a swirling, superheated disk of material around the event horizon. As this matter spirals inwards, it is compressed and heated to millions of degrees, blazing brighter than an entire galaxy before it finally crosses the point of no return. This process is both breathtakingly violent and frustratingly inefficient. There is a physical limit to how fast a black hole can feed a balancing act between the inward pull of gravity and the outward push of the intense radiation generated by the accretion disk itself. It is a cosmic equation that dictates a universal speed limit for growth. To grow a stellar mass black hole into a supermassive one, a Titan, 1,000,000 or even 1,000,000,000 times the mass of our Sun, you would need to feed it continuously at the maximum possible rate for billions of years. It's like trying to grow a redwood tree from a single seed in a single season. Physics itself seems to forbid it. And that brings us to the heart of our conundrum. Because when we peer back into this era into the cosmic dawn, we don't find the small stellar mass seeds we expect. We find the redwoods. We find monolithic black holes already hundreds of thousands, even millions of times the mass of our Sun. They are gravitational titans dwelling in the cores of the very first protogalaxies already fully formed, already dominating their cosmic environments. They are ancient kings ruling over kingdoms that have barely been born. This discovery is not a minor anomaly. It is a fundamental crisis in cosmology. It is as if we found a fossilized skyscraper in a geological layer teeming with the first single-celled organisms. It's a temporal paradox, an object that appears to be older than the time it had to grow. How is this possible? How in a universe only 400 million years old, a mere 3% of its current age, did these colossal engines of gravity assemble themselves? The slow, steady path of stellar collapse and gradual accretion simply does not work. The clock runs out. The math fails. The universe did not have the time. This isn't just an academic puzzle. It strikes at the core of our own cosmic history. Because we now understand that these supermassive black holes are not merely passive residents of their galaxies. They are the architects. Their immense gravity acts as a cosmic anchor, a seed around which the first galaxies coalesce. The unbelievable torrent of energy they blast out as they feed, known as quasar feedback, can regulate the birth of stars across their entire host galaxy, sometimes triggering furious bursts of star formation, other times blowing the precious gas away and sterilizing the galaxy for eons. The intricate dance between a galaxy and its central black hole is the primary engine of cosmic evolution. It dictates the size, the shape, and the ultimate fate of a galaxy like our own Milky Way. If we don't understand how these first black holes formed, we don't truly understand how the first galaxies formed. If we don't understand the beginning of the story, our entire narrative of the cosmos has a missing first chapter. For decades, theorists have wrestled with this paradox, proposing ever more exotic solutions. Perhaps the first stars were so mind-bogglingly huge thousands of times the mass of the Sun that when they collapsed, they bypassed the stellar mass phase, entirely forming intermediate mass black holes, bigger seeds to start with. This would give them a crucial head start. Or maybe in the densest, most violent corners of the early universe, vast clouds of primordial gas, millions of solar masses in size, could have sidestepped the star formation process altogether, undergoing a terrifying event known as direct collapse. Imagine an entire stellar nursery, a cloud destined to form 1,000,000 suns instead, collapsing in on itself in a single calamitous gravitational event, forging a monolithic black hole in one spectacular step. These heavy seed theories are compelling, but they require a perfect storm of conditions, a set of cosmic circumstances so rare they may have only happened a handful of times in the observable universe. They are theories born of necessity, attempts to explain an observation that seems to defy our standard cosmological model. For years, this has been a battle fought with computer simulations and theoretical models, a ghost hunt in the dark. The evidence was always just out of reach. The light from that era, too faint, too stretched by cosmic expansion, for our telescopes to capture with clarity. We were looking for the faintest of whispers from the very beginning of time, drowned out by the chorus of 100 billion younger, brighter galaxies. We needed a new eye on the universe, an instrument so powerful, so sensitive it could part the veils of time and space and stare directly into the cosmic nursery. We needed a time machine, and now we have one. The James Webb Space Telescope with its golden honeycomb mirror is designed for precisely this mission, to capture the faint infrared glow of the most distant objects in creation. And it has found something. A single point of light. A ghost from a forgotten age. Deep within the data, a team of astronomers has uncovered a signal, the unmistakable fingerprint of a ravenous supermassive black hole, seen as it was just 400 million years after the Big Bang. It is the oldest, most distant, most primordial black hole we have ever seen. This single discovery is not just another astronomical record. It is a Rosetta Stone for the cosmic dawn. It is a direct physical relic from the age of monsters, a laboratory for testing our most fundamental ideas about how the universe came to be. By studying this one object, this solitary gravitational titan, we can begin to answer the impossible question. Was it born from the collapse of a hypergiant star? Or did it spring into existence from the cataclysmic collapse of a primordial gas cloud? The clues are imprinted in the light surrounding it, in the chemistry of the gas it is consuming, in the nature of the tiny embryonic galaxy it calls home. The story of this one black hole is the story of them all. It is the key to understanding the hidden architecture of the cosmos, the secret of how galaxies grew from faint chaotic clouds of gas into the majestic spirals that fill our skies today. We stand on the precipice of a revolution in our understanding. The search is no longer theoretical. The hunt is on. We are about to follow the light from this ancient phantom back through 13.4 billion years of cosmic history, to witness its birth, and in doing so to witness the dawning of our own universe. The cosmic rulebook is about to be rewritten. The story starts now. What if the universe keeps a secret diary written in the language of gravity and light? What if we could find its earliest entry penned when the cosmos was just an infant still shrouded in darkness? We have long searched for the first galaxies, the first stars, the first light. But we are now discovering something else entirely. We are finding monsters lurking in the crib of creation. Monsters that by all our cosmic logic should not exist. Their presence forces us to question not just how the universe began, but how quickly it became the violent, structured, and magnificent place we know. The story of these impossible beasts begins where all stories do at the very beginning. Imagine a point of no dimension, a state of infinite temperature and density. This is not an explosion in space, but an explosion of space itself. It is the genesis moment, the Big Bang. In the first incandescent fractions of a second, the universe was a seething uniform soup of fundamental particles and energy governed by laws so extreme they are still on the very edge of our comprehension. There were no atoms, no stars, no galaxies. There was only potential and a ferocious outward surge that we call cosmic inflation, an expansion so violent it stretched a subatomic speck to a cosmic scale, in less than the blink of an eye. This act of unimaginable stretching smoothed out the fabric of space-time, yet left behind the faintest of quantum whispers, tiny, almost imperceptible wrinkles in the density of the early cosmos. These minute imperfections, these ghostly echoes of quantum chaos, would one day become everything we see. They were the seeds of destiny sown in the first instant of time. As the universe continued to expand, it cooled. The inferno subsided. Energy congealed into matter. Protons and neutrons formed, and within minutes they fused into the simplest atomic nuclei, mostly hydrogen and helium, the raw elements from which all future complexity would be forged. For 380,000 years, this primordial plasma remained an opaque fog. Light in the form of photons was trapped in a perpetual game of pinball, constantly scattering off free-roaming electrons, unable to travel any meaningful distance. The entire universe was a glowing, impenetrable haze, but as the expansion continued its relentless work, the cosmos cooled enough for a monumental event to occur: recombination. Electrons were finally captured by atomic nuclei, forming the first stable neutral atoms. For the very first time, light was set free. This event, this great decoupling, is a moment we can still see today, frozen in time. It is the cosmic microwave background, the oldest light in the universe, a faint residual afterglow of creation that permeates all of space. And with its release, a curtain fell. The age of a light gave way to an era of profound and absolute blackness. The cosmic dark ages had begun. For hundreds of millions of years, the universe was an abyss, an almost featureless expanse of neutral hydrogen and helium gas expanding and cooling in an unbroken starless night. Imagine an ocean without shores, a silence without end. The only thing happening was the impossibly slow and patient work of gravity. Those tiny density wrinkles left over from the Big Bang, those quantum whispers, were now exercising their faint but inexorable pull. In regions where the gas was infinitesimally denser, gravity's hold was infinitesimally stronger. Over eons, this subtle advantage compounded. Gravity, the silent architect of the cosmos, began to gather the diffuse veils of hydrogen, pulling them into vast gossamer filaments, a cosmic web of dark matter and primordial gas taking shape in the void. Where these filaments intersected the densest knots of matter, began to form, pulling in more and more material, growing ever more massive. These were the proto-galactic nurseries, the crucibles where the universe would finally break its long silence and create light anew. Inside these collapsing clouds, the pressure and temperature began to rise, climbing higher and higher, until in the very heart of the densest cores, a new fire was lit. The threshold for nuclear fusion was crossed. Hydrogen atoms were crushed together to form helium, releasing a torrent of energy and light. The first stars had ignited. These were not stars like our sun. They were beings of a different order entirely, a lost generation of celestial titans known as Population 3 stars. Forged from pure, unadulterated hydrogen and helium, the pristine material of the Big Bang, they were uncontaminated by the heavier elements that later stars would contain. This elemental purity had a profound consequence. It allowed them to grow to sizes we can barely imagine today. They were colossal spheres of incandescent gas, hundreds, perhaps even 1,000 times the mass of our own sun. They burned not yellow or orange, but a brilliant searing blue-white with surface temperatures so extreme they would act as celestial blowtorches, sterilizing their cosmic neighborhoods with overwhelming floods of ultraviolet radiation. But their magnificent power came at a terrible cost. They lived furiously, burning through their vast reserves of nuclear fuel in only a few million years, a fleeting instant on the cosmic timescale. Their deaths were as spectacular as their lives. Having exhausted their fuel, these leviathans could no longer support their own unimaginable weight. The outer layers collapsed inward at unbelievable speeds, crushing the stellar core into an object of impossible density. The resulting explosion of hypernova was a cataclysm of unparalleled violence, briefly outshining entire infant galaxies. And in the aftermath of that firestorm, something new was left behind. The crushed remnant of the star's core, a point of such immense gravity that nothing, not even light itself, could escape. The universe had just forged its very first black holes. These were the first seeds, the stellar mass remnants of the first generation of stars. Each one perhaps 100 times the mass of our sun. They were the universe's first true monsters, born from fire and gravitational collapse. They began to drift through the chaotic environments of the first galaxies, their powerful gravity acting as an anchor pulling in surrounding gas and the debris of other stars. This process of consumption, known as accretion, is how a black hole grows. As material falls inward, it forms a swirling, superheated disk, an accretion disk that glows with ferocious intensity before finally crossing the event horizon, the point of no return. This is one clear path to creating a black hole in the early cosmos. A seed is planted by the death of a truly massive star, and then it begins to feed slowly but surely, growing over time. For decades, this was considered the standard model, the most logical and straightforward way to begin building the cosmic giants we see today. But as our vision into the deep past sharpened, a troubling question began to emerge. Was this path fast enough? The violence and sheer scale of the early universe suggested another far more dramatic possibility, a path that skipped the stellar phase altogether. Imagine one of those primordial clouds of gas, one of the vast nurseries destined to form the first stars. But imagine this cloud is special. It is immense, containing the mass of 100,000 suns. And it is pristine, composed of nothing but hydrogen and helium. Under normal circumstances, this cloud would cool and fragment as it collapsed, splintering into thousands of smaller clumps that would each form an individual population 3 star. But what if something prevented that from happening? What if a nearby cluster of the first stars already blazing away bathed this particular cloud in an intense, overwhelming bath of ultraviolet radiation? This radiation would act like a cosmic sterilizer, breaking apart the fragile hydrogen molecules that are essential for the gas to cool efficiently. Without this cooling mechanism, the cloud cannot fragment. It cannot break apart. Instead, the entire colossal structure, all 100,000 solar masses of it, continues to collapse as a single coherent entity. The core temperature and pressure skyrocket past the point of nuclear fusion, past any stable state a star could ever achieve. The cloud collapses catastrophically uncontrollably under its own colossal weight. It collapses directly into a black hole. This is the theory of the direct collapse black hole, a far rarer, more exotic and monumentally more potent method of seeding the cosmos with monsters. It bypasses the need for a star to live and die, instead forging a heavy seed in one swift gravitational implosion. Where the remnant of a population 3 star might provide a seed of 100 solar masses, a direct collapse event could create a seed of 100,000 solar masses from the very beginning. It's the difference between planting an acorn and planting a sapling that's already 20 feet tall. It gives the universe a tremendous head start in the race to build the supermassive black holes we observe at the hearts of nearly every major galaxy, including our own Milky Way. These two pathways, the death of the first stars and the direct collapse of primordial gas, became the leading explanations for the origins of the cosmic titans. One common and producing small seeds, the other rare but producing massive ones. For a time, it seemed that between them they could explain the evolutionary ladder of black holes from these humble beginnings to the billion solar mass behemoths of the later universe. But the universe, it turns in, had a surprise for us. A temporal paradox hidden in the deepest, earliest recesses of time. A discovery that would challenge the very limits of these elegant theories. We are confronted now with the time problem, a cosmological conundrum of the highest order. Our telescopes, especially the James Webb Space Telescope, are time machines. They peer so far out into space that they see the universe as it was not as it is. They are capturing photons that have been travelling towards us for over 13 billion years. And in that ancient light, we are finding things that should not be there. We are discovering quasars, the intensely luminous signatures of actively feeding supermassive black holes, shining brightly when the universe was less than 1 billion years old. These are not seed black holes. These are fully formed giants, hundreds of millions, even billions of times the mass of our Sun. And this is where our story hits a wall. The timeline does not add up. A black hole cannot grow infinitely fast. There is a physical speed limit to its consumption, a principle known as the Eddington limit. As gas falls towards a black hole, the light and radiation blasting out from its superheated accretion disk exerts an outward pressure. If the black hole tries to feed too quickly, this radiation pressure becomes so intense that it literally blows away the incoming fuel, choking off its own food supply. It's like trying to drink from a fire hose that is actively pushing you away. This limit dictates the maximum rate at which any black hole can grow. When we apply this cosmic speed limit to our models, the numbers refuse to cooperate. Let's take the first path, the seed black hole, from a population 3 star, 100 times the mass of the Sun. Even if this seed fed continuously without interruption at the absolute maximum Eddington limit, from the moment it was born, it simply did not have enough time. To grow to 1 billion solar masses in just a few 100 million years is a mathematical impossibility. It would be like a human infant growing to the size of a blue whale in its first month of life. The timeline is too short. The growth required is too extreme. So what about the other path, the direct collapse seeds? At 100,000 solar masses, they certainly have a significant head start. They make the problem less severe, but they do not solve it entirely. To reach the masses we observe in the time available, these heavy seeds would also need to sustain near-perfect maximum efficiency feeding for their entire existence. This requires a constant, impossibly dense supply of gas funneled directly to them, a Goldilocks scenario of cosmic proportions that must happen immediately after their formation. And even then, for the most massive and most ancient black holes we are now finding, the numbers are still uncomfortably tight. The timeline remains a profound, nagging contradiction. We are left with a stark and thrilling mystery. The evidence is right there, shining at us. From across 13 billion years of cosmic history, monsters were born early, and they grew impossibly fast. The simple, elegant pathways we had constructed for their creation are straining at the seams, perhaps even breaking. We are forced to ask new, more radical questions. Is our understanding of accretion fundamentally incomplete? Could black holes in the dense, chaotic early universe have found ways to circumvent the Eddington limit, to engage in a form of super Eddington binge eating that our physics does not yet allow for? Or perhaps there was a third path of formation, a mechanism for creating even more massive seeds that we haven't even conceived of yet, born from physics, unique to that primordial epoch. Or most unsettling of all, could the seeds themselves be even older? Is it possible that some black holes weren't forged in the collapse of gas or stars at all, but were instead primordial black holes, forged directly from the exotic pressures and energies of the Big Bang itself? The existence of these ancient titans serves as a direct challenge to our cosmological models. And one recent discovery, the subject of our investigation, has sharpened this challenge into a crisis. A black hole has been found residing in a galaxy just 400 million years after the Big Bang. It is a cosmic fossil from the edge of the Dark Ages, an object whose very existence defies the tyranny of time and demands a new chapter be written in our story of the cosmos. To have found such a behemoth lurking in the cradle of time was not just a discovery, it was a profound and unsettling accusation. It accused our most cherished theories of being incomplete, our understanding of cosmic evolution of being naive. It forced upon us a question that for generations we believed we had postponed for a distant future, a future with better tools and clearer sight. That question was no longer hypothetical. It was a direct challenge screaming at us from across 13 billion years of expanding space. How do you build a monster in the dark? To even begin to answer this, you must first understand the journey we took to find it. This was not a casual glance through a garden telescope. It was a multi-generational quest, a pilgrimage to the very edge of reality, to a time so remote it is known not as history, but as an epoch, the cosmic dawn. Imagine the universe as a vast dark ocean, and the Big Bang as a singular brilliant flash beneath its surface. For a time after that flash, the ocean was opaque, a superheated fog of plasma, where light was trapped endlessly, scattering off free electrons unable to travel. This was the cosmic dark age, an era of impenetrable gloom. But as the universe expanded and cooled, atoms formed, the fog cleared, and for the very first time the light from the first stars and galaxies was free to begin its journey across the cosmos. That first sunrise, the moment the universe switched on its lights, is the cosmic dawn. Seeing it has been the holiest of grails for astronomy. For decades we strained our eyes, building ever larger temples of glass and steel on remote mountaintops, all pointed toward that primordial shore. Our greatest champion in this endeavour was the Hubble Space Telescope. For 30 years it was our window, a breathtaking portal to the heavens. Hubble showed us galaxies in their adolescence, in their turbulent star-forming youth. It took us back billions of years, revealing the grand tapestry of cosmic structure. It performed feats that redefined our place in the universe. But even Hubble had a wall it could not see beyond. It was a champion of visible and ultraviolet light, the colours our own eyes perceive. Yet the very nature of the universe conspired against it in this ultimate quest. The expansion of space-time itself acts as a cosmic filter. As light travels from the farthest reaches of the universe, the fabric of space it journeys through is stretching. This stretching pulls on the light waves, lengthening them, shifting them down the electromagnetic spectrum. It's a phenomenon known as cosmological redshift. The brilliant blue and white light of a newborn star after a journey of over 13 billion years arrives at our doorstep not as visible light, but as the faint invisible glow of infrared. The cosmic dawn wasn't just far away in space, it was hidden from Hubble behind an infrared veil. Trying to see the first galaxies with Hubble was like trying to listen to a symphony through a wall that only lets the lowest bass notes pass. You know, something magnificent is happening. You can feel the faint vibrations, but the melody, the richness, the story is lost. We could see the blurry outlines of galaxies from when the universe was perhaps 1 billion years old, but the crucial era, the first few 100 million years, remained shrouded in mystery. The nursery of creation was closed to us. We were staring at a locked door, and for a long time we had no key. The solution, therefore, had to be audacious. It couldn't be another telescope on a mountain peering through our own planet's shimmering, distorting atmosphere. It couldn't even be another Hubble, a magnificent but ultimately limited instrument in low Earth orbit. We needed a new kind of eye, an eye that could see the invisible, an eye that could capture the faintest, most ancient heat from the dawn of time. We needed a time machine built of gold and beryllium. We needed the James Webb Space Telescope. To call JWST a successor to Hubble is a profound understatement. It is a different order of being entirely. Its primary mirror, a breathtaking mosaic of 18 gold-coated hexagonal segments, stretches over 6.5 meters across a golden honeycomb designed to catch the whispers of ancient light. It is so large it had to be folded like cosmic origami to fit inside its launch rocket. Its destination was not near Earth, but a lonely gravitationally stable point 1 million miles away, a place called the Second Lagrange Point, or L2. Here it could orbit the Sun in lockstep with the Earth using a colossal 5-layer sun shield the size of a tennis court to block the light and heat from the Sun, Earth and Moon. This shield is a masterpiece of thermal engineering, creating a permanent deep space shadow where the telescope could cool to unimaginably frigid temperatures, just tens of degrees above absolute zero. This extreme cold is not an incidental detail. It is the secret to its power. JWST is designed to see in the infrared to detect faint heat. If the telescope itself were warm, its own glow would blind it like trying to photograph a candle flame from inside a blast furnace. It had to become colder and darker than anything around it to see the faint embers of the cosmic dawn. The journey and deployment of this machine was one of the most complex and nail-biting engineering feats in human history. Hundreds of single points of failure, any one of which could have turned our golden eye into a multi-billion-dollar piece of space debris. The unfolding of the sunshield, the locking of the mirror segments, the calibration of its instruments all happened silently, autonomously, 1 million miles from any human hand. The world's scientific community held its collective breath. Generations of careers, the hopes of thousands of scientists, and our deepest questions about our own origins all rode on this delicate remote-controlled celestial ballet. And then, after months of agonizing waiting, it worked. The eye opened, and the universe we thought we knew was shattered forever. The first deep field images that JWST sent back were not just improvements on Hubble's. They were a revelation, a complete paradigm shift. Where Hubble saw a few faint smudges in the darkness, JWST revealed a tapestry teeming with galaxies, thousands upon thousands of them, each a brilliant ruby-red ember, their light stretched and warped by their immense journey through time. The sheer number of them was the first shock. The early universe was far more crowded, far more industrious than our models had ever predicted. The cosmic dark ages seemed to end almost as soon as they began, with galaxies igniting across the cosmos with ferocious speed and intensity. These were not the small, disorganized proto-galaxies we expected to find. Many were surprisingly large, with discernible structures, spiral arms and galactic bars already taking shape. It was like looking at photographs of what should have been infants, and finding them already behaving like well-developed adolescents. The universe, it seemed, was in a hurry. But amid this stunning new galactic census, astronomers began to notice something else. Something unusual. Scattered among the reddish glow of these nascent star systems were objects that didn't look like galaxies at all. They were pinpricks of ferocious, almost violent light. Points of such impossible brilliance, they seemed to burn holes in the fabric of the image, outshining the combined light of all the billions of stars in their host galaxies. These were the telltale signatures of quasars. The term is a shortening of quasi-stellar radio source. a name from a time when we didn't know what they were, only that they were point-like like stars but weren't. We now know them to be something far more terrifying and magnificent. A quasar is not a thing, but an event. It is the blinding flash of a supermassive black hole at the centre of a galaxy actively and voraciously feeding on a colossal disk of gas dust and shredded stars. This material, in a process called accretion, doesn't simply fall in. It spirals inward, forming a vast flat disk, a cosmic whirlpool of unimaginable scale. As this matter accelerates to near the speed of the light friction, and magnetic forces heat it to millions of degrees, turning it into a celestial blowtorch that unleashes more energy into the universe than entire galaxies combined. This is the light of an active galactic nucleus, or AGN. It is the shriek of matter being annihilated at the edge of forever. Previous telescopes had found quasars, but only in the more recent cosmic past, billions of years after the Big Bang, giving black holes what we thought was ample time to grow. But JWST, with its infrared vision, began spotting the red-shifted glare of these cosmic engines deeper and deeper in time. Its powerful spectrographs, like the Near-Infrared Spectrograph or NIR SPEC, could act as cosmic prisms, taking the light from a single distant point and splitting it into its constituent wavelengths, a rainbow of information. In that spectrum, scientists could see the unmistakable fingerprint of a quasar, the broad, smeared-out emission lines of superheated gas swirling at incredible velocities. It was a gravitational speed gun measuring the frantic dance of matter in the grip of a colossal central object. The data was unequivocal. These were not just bright galaxies. They were active, feeding, growing, supermassive black holes. The team pushed the telescope's capabilities to their absolute limit, staring at blank patches of sky for hundreds of hours, accumulating photon by photon, the ghostly light from the edge of time. They found quasars at a redshift corresponding to 700 million years after the Big Bang, then 600 million, then an object named J0313 1806, a blazing quasar powered by a 1.6 billion solar mass black hole, seen when the universe was just 670 million years old. Each new discovery was a new record, a new challenge to our theories. And then they found the one at the heart of our story, a brilliant beacon in the galaxy GNZ11. The spectrum came back clear, haunting, and utterly undeniable. Its light had travelled for so long that we were seeing it as it was a mere 400 million years after the universe began. The cosmic dawn had barely broken. The first galaxies were just coalescing from the primordial mist. And yet here was a black hole already 2 million times the mass of our Sun, and it was feeding so rapidly it was practically incandescent. This is where the quiet satisfaction of discovery curdled into a profound sense of scientific crisis. Because according to everything we thought we knew, this should not be possible. The established narrative for how supermassive black holes form was a story of patience and gradual accumulation. It begins with a single massive star, perhaps 100 times the mass of our Sun, living a short, brilliant life, and then collapsing under its own gravity to form a stellar mass black hole. This is the seed. To grow into a supermassive monster, this seed needs to feed. It must slowly sip from the interstellar gas around it, or more efficiently merge with other black holes. Over hundreds of millions, even billions of years through countless mergers and feeding events, this seed could theoretically grow into the titans we see at the centres of galaxies like our own Milky Way. It's a process of slow, steady, hierarchical growth, like a single raindrop joining a puddle, which flows into a stream, then a river, and finally the ocean. The model is elegant, logical, and it works beautifully to explain the black holes we see in the local modern universe. But the discovery in GNZ11 and others like it took a sledgehammer to this elegant picture. The timeline simply does not add up. 400 million years is not enough time. It's cosmic infancy. To grow a black hole of millions of solar masses from a stellar seed in such a short period would require it to feed at a rate so extreme, so far beyond what we thought possible that it would violate its own physical limits. An accreting black hole can become so bright that the outward pressure of its own light literally blows away the very gas it is trying to consume. This is the Eddington limit, a kind of cosmic self-regulation. To grow as fast as the JWST observations demanded, these early black holes would have had to somehow bypass this fundamental physical law, feeding continuously at a gluttonous, impossible rate. It's like finding a 300-foot-tall sequoia tree that is only 2 years old. You know with absolute certainty that it could not have grown from a normal seed in that amount of time. The process itself is too slow. Something is fundamentally wrong with your understanding of how trees grow. This is the precipice where we now stand. The data from JWST did not simply add a new chapter to our story of the cosmos. It ripped out the opening pages and set them on fire. The comforting, gradualist model of black hole formation was buckling under the weight of this new impossible evidence. The presence of these ancient titans suggested that the universe didn't start with seeds. It started with giants. But how, if they didn't grow from the corpses of the first stars, where did they come from? Were they born different, forged in the cataclysmic collapse of unimaginable clouds of primordial gas? Or were they something even more exotic, a relic from an even earlier time? The discovery was not an answer. It was a declaration that our deepest cosmological models were broken. The comfortable narrative had collapsed, and in its place a thrilling, terrifying void of uncertainty had opened. We were faced with a stark choice: either our understanding of accretion physics was wrong, or the very origin story of black holes, one of the fundamental pillars of astrophysics, needed to be completely rewritten. The hunt for the monster had succeeded. Now we had to confront the far more difficult task of explaining it. And so the theoretical crisis demanded an answer from the universe itself. The elegant equations, the sophisticated simulations, all of them had led to a single glaring paradox. A ghost in the cosmic machine. What we needed was not another model but a witness. An artifact from that primordial era, a single point of light to confirm our deepest fears or restore our understanding. The search was on, not for a needle in a haystack, but for a whisper in a cosmic hurricane. The target was a faint, unassuming smudge of crimson, a candidate galaxy known to astronomers as GNZ11. First spotted by Hubble, it was already famous, holding the record for the most distant and therefore oldest galaxy ever seen. It was a mere pixel, a ghost on the edge of vision, tantalizingly close to that enigmatic dawn. But Hubble, for all its revolutionary power, could only see so much. It had glimpsed the house, but it couldn't see the fire burning within. To do that, we needed an eye that could pierce the veil of time and dust, an instrument tuned to the faded, stretched-out light of the beginning. We needed the James Webb Space Telescope. When Webb turned its golden gaze towards that precise lonely coordinate in the constellation Ursa Major, it wasn't just another observation. It was a deliberate act of cosmic archaeology. For months, the mission planners, the astronomers, the engineers all held their collective breath. They were aiming their billion-dollar time machine at a target over 13 billion light-years away, hoping to catch a photon that had been travelling since the universe was a mere infant. A photon that began its journey long before our own sun had even begun to coalesce from its nebula cradle. The light that finally fell upon Webb's detectors was impossibly ancient, a fragile relic of a bygone eternity. It carried within its very wavelength the story of its origin, a message stretched and distorted by the expansion of space-time itself. The initial images were staggering, resolving that faint red smudge into a structured, albeit chaotic, primordial island of stars. Here was a city of suns alive and turbulent in an age when we expected only scattered villages. But the true revelation was not in the picture. It was hidden within the light itself. The real work began when scientists engaged one of Webb's most powerful instruments, the near-infrared spectrograph, or NIR spec. This is not a camera that takes a picture. It is a prism of almost magical sensitivity. It catches the ancient light and shatters it, spreading it out into its constituent colours, a rainbow from the dawn of time. And within that rainbow, that spectrum is a code. It's a cosmic barcode imprinted with the chemical fingerprints of the elements that created and absorbed the light. As the data streamed back to Earth across the unimaginable gulf of space teams of astrophysicists gathered around their monitors, what they were looking for were specific dark lines, tiny gaps in the otherwise continuous spectrum. These are absorption lines, signatures left by atoms like hydrogen and oxygen, which absorb light at very specific known frequencies. But in the light from GNZ11, these familiar lines were not where they were supposed to be. They had been shifted, pushed dramatically towards the red end of the spectrum. This is the cosmic echo of a siren speeding away from you, its pitch dropping as it recedes. For light, this change in pitch is a change in colour. It is redshift, the unambiguous, unimpeachable proof of cosmic expansion. By measuring precisely how far these spectral lines had been shifted, we could calculate the object's recession velocity. And from that velocity, using the known laws of cosmic expansion, we could determine its distance with breathtaking accuracy. From its distance, we could finally definitively calculate its age. The numbers that emerged from the analysis were at first hard to comprehend. The redshift was an astonishing 10.6. This simple number, this measurement of stretched light, was a verdict delivered by the cosmos. It confirmed that the light from the heart of GNZ11 had travelled for 13.4 billion years. It was a snapshot of the universe as it existed just 400 million years after the Big Bang. 400 million years. The number hangs in the air, almost meaningless in its scale. Imagine the entire 13.8 billion year history of the universe compressed into a single calendar year. The Big Bang is the first second of January 1st. The formation of the Milky Way happens in early March. The Earth and our solar system don't appear until early September. All of recorded human history from the first cave paintings to this very moment would occupy the final 10 seconds of New Year's Eve. In this cosmic year, the light from GNZ11 was emitted on January 10th. We were staring into the crib of the cosmos. This alone was a monumental achievement, a new record for the oldest object ever confirmed. But as the teams dug deeper into that spectral barcode, a far more unsettling picture began to emerge. The light wasn't just the gentle scattered glow of infant stars. There was something else in the data, something violent and overwhelmingly powerful. The spectrum showed evidence of gas moving at incredible speeds, hundreds of kilometers per second. This was not the stately rotation of a nascent galaxy. This was chaos. This was gas being superheated to millions of degrees, energized to the point that it shone with an almost impossible ferocity. This was the signature of an accretion disk, the telltale sign of matter being torn apart as it spirals into the abyss of a supermassive black hole. Hidden in the heart of this infant galaxy in the first 10 days of the cosmic year was a monster. The very existence of a black hole this early was shocking enough. But the true crisis, the moment the time problem, ceased to be a theoretical puzzle and became a cold, hard observational fact, came when they calculated its mass. How do you weigh an object you cannot see across a distance of 13 billion light-years? You measure its influence. You look at the sheer brightness of the light it is generating. The light from GNZ11's core was not just bright, it was blinding. It outshone all the galaxy's billions of young stars combined. This celestial blowtorch, this quasar, was a beacon screaming across the cosmos, and the luminosity of a quasar is directly proportional to the rate at which its central black hole is feeding. There is a physical limit to how fast a black hole can grow, a speed limit imposed by physics itself called the Eddington limit. The outward pressure of the light generated by the infalling matter pushes back against the inward pull of gravity. If a black hole feeds too fast, it will literally blow its food away. So by measuring the quasar's brightness, the scientists could calculate the minimum rate of consumption, and from that rate working backward, they could calculate the absolute minimum mass the black hole must have to sustain such a feast. It was like deducing the size of a whale by the size of the wake it leaves in the water. The result of this calculation was the shot that shattered the foundations of cosmology. The black hole at the heart of GNZ11 weighed in at approximately 1.6 million times the mass of our own Sun. 1.6 million. Let that sink in. Not a stellar mass black hole born from a single dead star. Not even an intermediate one a few thousand times our Sun's mass. This was a fully fledged supermassive black hole, already a cosmic titan in an era when it could not exist. It was like finding a fully grown redwood tree that was only 3 weeks old. The discovery transformed the abstract into the undeniable. The smooth, gradual growth curves predicted by our theories, the ones that had been trusted for decades, were not just wrong, they were laughably, impossibly wrong. According to those theories, to reach 1 million solar masses, a black hole starting from a single large star would need to feed continuously at the absolute maximum physical limit for nearly 1 billion years. But this black hole had only 400 million years to work with from the moment the first stars even flickered into existence. There wasn't enough time, there wasn't enough matter. The universe was simply too young. It was a temporal impossibility, an object that existed before it had the time to be born. Suddenly every textbook had a chapter that was obsolete. Every computer simulation of galaxy formation was based on a flawed premise. The comfortable step-by-step story we had told ourselves about the universe's adolescence had been torn apart by a single inconvenient fact. This wasn't just another data point, it was a revolution. It was the observational proof that our understanding of cosmic origins was fundamentally incomplete. The discovery of this impossible object did not solve a mystery. It created a dozen new, more profound ones. It was no longer a question of if. Our models were wrong, but how they were wrong. What fundamental force, what unknown mechanism, what exotic process were we missing? How can the universe build monsters in the dark, in near silence, and in the blink of a cosmic eye? The ghost in the machine was no longer a ghost. It was real. It had a name, a location, and a weight. And it was staring back at us from across the abyss of time, a silent challenge to everything we thought we knew. The neatly paved road of cosmic history had just crumbled away, revealing a chasm of ignorance beneath our feet. We now had to confront the radical, uncomfortable truth that the universe's earliest chapters were far more violent, more rapid, and more mysterious than we had ever dared to imagine. The age of innocence in cosmology was over. The real work, the search for a new story of creation, was only just beginning. The signal was unmistakable, a spectre of gravity haunting the dawn of time. But as the initial wave of elation subsided among the teams, who found it a deeper, more unsettling emotion, began to ripple through the world of astrophysics. It was a feeling of profound intellectual vertigo. The discovery was not just a new entry in the cosmic catalogue. It was a declaration of war against our most fundamental timelines. Every textbook, every simulation, every carefully constructed theory of cosmic evolution was built upon a foundational assumption that growth takes time. Galaxies assemble piece by piece, stars ignite, live and die in a stately procession, and the universe's largest black holes we believed were patient titans, growing over billions of years from humble stellar remnants. This discovery tore that assumption to shreds. We were now staring at a fully formed giant weighing billions of suns in a universe that was barely an adolescent. It was the cosmological equivalent of finding an ancient oak tree sprouted to its full height just a week after the seed was planted. The models didn't just bend, they shattered. Across the globe, theorists and observers scrambled not to celebrate, but to explain an object that by all rights simply should not exist. The question echoed in virtual meetings and frantic email chains: how do you build a monster in the dark? The heart of the problem lies with the seed. To grow a supermassive black hole, you must first plant one. For decades, the leading theory was elegant in its simplicity. The very first stars, known as population 3 stars, were behemoths, hundreds of times more massive than our own sun. When these short-lived giants died, they collapsed into the first black holes, the light seeds, for everything that would follow. Yet these initial seeds, for all their stellar grandeur, were cosmic lightweights, weighing in at perhaps 100 solar masses. To get from that to the billion solar mass Titan we had just found would require a growth rate so ferocious, so sustained, it bordered on physical impossibility. It demanded an answer to a chilling question: what if the seeds weren't light at all? What if the universe had a way to skip the stellar phase entirely to conjure giants from the very beginning? This radical idea gave birth to the hypothesis of the heavy seed, a process known as direct collapse. It is a theory born of cosmic extremes requiring a perfect storm of conditions that may have only existed in a few hallowed corners of the infant cosmos. Picture a vast primordial cloud of gas 1,000,000 times the mass of our sun drifting through the dark ages before galaxies are truly ignited. This cloud is pristine, composed of only the hydrogen and helium forged in the Big Bang. It is almost completely devoid of heavier elements or metals, which in astrophysics are the crucial cooling agents that allow gas to fragment and form stars. Without these metals, the cloud is trapped in a state of rising pressure. It cannot easily shed its heat. It cannot break apart into thousands of stellar nurseries. But this alone is not enough. To prevent even a single star from forming, which would contaminate the cloud, you need another more violent ingredient. You need a celestial blowtorch. Imagine our pristine cloud has a neighbour, a brilliant newly forming galaxy blazing with the light of thousands of massive blue-hot stars. This neighbouring galaxy bombards our cloud with a torrent of ultraviolet radiation, a relentless flood of high-energy photons. This radiation acts as a sterilising agent. It blasts apart any fragile molecules of hydrogen that might form, which are the final essential coolant needed for starbirth. The cloud is now trapped in a cosmic pressure cooker. It can't cool, it can't fragment. It can only contract under its own immense gravity, getting hotter and denser, the entire million solar mass structure collapsing inward as a single colossal object. The core temperature skyrockets past millions of degrees, but with no way to ignite nuclear fusion across its vast expanse, and with its escape velocity climbing to unimaginable speeds, the cloud faces only one fate. It collapses past the point of no return. It forms a black hole not from the death of a star, but from the stillbirth of an entire galaxy's worth of stars. In a single cataclysmic moment, a heavy seed is born, weighing in at 100,000 times the mass of the Sun. It's a shortcut, a way to jumpstart the cosmic clock. With a progenitor of this size, the path to 1 billion solar masses becomes dramatically less challenging, the timeline suddenly more plausible. It is a beautiful and compelling solution, but it is also frighteningly delicate. The conditions required, the massive pristine cloud, the perfectly distanced, intensely radiating neighbour, are so specific, so rare, that many simulations suggest such perfect alignments might never have happened. Was our newfound giant the product of an almost impossibly rare confluence of events, or was there another more brutal path to assembling a monster? If the universe couldn't create a giant in one fell swoop, perhaps it could build one through relentless savage cannibalism. This leads us to the second major hypothesis, a runaway chain of mergers. This scenario begins back with the conventional light seeds, the black holes left over from the first generation of stars. But instead of a single seed growing in isolation, we must imagine hundreds or even thousands of them born inside an incredibly dense, compact environment. Think of it as the core of a protogalaxy or a nascent globular cluster, a churning, chaotic stellar metropolis packed into a space barely a few light-years across. Here, gravity is the undisputed tyrant. The newly formed black holes, being the most massive objects around, begin to sink toward the centre of this gravitational whirlpool. Through a process called dynamical friction, they shed their orbital energy to the surrounding stars, spiralling inward like stones in a vortex. What follows is a demolition derby on a cosmic scale. As these black holes congregate in the core, their orbits decay. They draw closer, locked in a gravitational dance that can only end in collision. Two black holes merge, creating a new, more massive one. This victor, with its enhanced gravitational pull, has an even greater advantage, more readily capturing its smaller brethren. It's a process of violent accretion, a chain reaction of mergers. Each collision sends a powerful shudder through space-time, a gravitational wave carrying away energy and information about the cosmic violence that birthed it. For this runaway process to work within the universe's tight time limit, the mergers would have to happen with breathtaking frequency. A constant procession of black holes, one after another, feeding the ever-growing monster at the centre. This vision has the advantage of relying on physics we understand well, stellar evolution, and gravitational dynamics. There are no exotic pristine clouds or perfectly aimed radiation fields required. There is only gravity red in tooth and claw. But the challenges are just as formidable. Each time two black holes merge, the resulting gravitational waves are not perfectly symmetrical. They create a kick, a recoil that can send the newly merged black hole flying out of the cluster at incredible speeds. If the kick is too strong, the growing seed is ejected from its own nursery, starving it of the very fuel it needs to continue its rampage. The cluster must be massive enough, its gravitational grip strong enough to hold onto its prized monster. Furthermore, the sheer efficiency required is staggering. The cluster would have to funnel its black holes to the centre at a rate that defies many of our simulations. Could such a dense sacrificial star cluster even hold itself together long enough to feed the runaway, or would it simply puff up and evaporate under the strain of such internal violence? It is a plausible yet deeply problematic path paved with the corpses of countless black holes, a testament to nature's capacity for building through destruction. But as physicists stared into the abyss of this timeline, another far more speculative possibility began to be whispered. What if the seed wasn't forged in the early universe at all? What if it was a relic from the universe's very first breath? This is the most exotic and mind-bending of the hypotheses, plunging us back into the first second of cosmic history. Here in the roiling high-energy plasma of the newborn universe, the cosmos was not perfectly smooth. Quantum fluctuations created regions of infinitesimally higher density. In this era of extreme pressure and energy, it is theorized that some of these overdense regions could have collapsed under their own gravity, punching a hole in spacetime itself. These would not be black holes from collapsed matter as we know it. They would be primordial black holes, or PBHs, forged directly from the fabric of the universe in its most extreme state. Unlike stellar black holes, which have a lower mass limit, PBHs could theoretically form with any mass from that of an asteroid to thousands of suns. If a sufficiently massive primordial black hole was created in that first instant, it would have existed through the dark ages as a prepackaged seed, a gravitational anchor, waiting patiently for the first gas clouds to form and fall into its grasp. This idea elegantly sidesteps the entire formation problem. There is no need for pristine clouds or runaway mergers. The seed is simply a given a ghost from a time before time as we measure it. It offers a tantalizingly simple solution to an otherwise intractable problem. Yet for all its elegance, it remains on the furthest fringes of science. We have absolutely no direct evidence that primordial black holes exist. Their formation depends on physics, at energy scales we cannot replicate in an era of the universe we cannot directly see. Some theories link them to the mystery of dark matter, suggesting these ancient relics could make up the unseen mass of the cosmos. But as an explanation for our ancient giant, it requires us to accept an extraordinary premise to solve an extraordinary problem. We would be explaining one mystery by invoking another deeper one. A seed from a direct collapse, a seed from 1,000 mergers, or a seed from the beginning of time itself. Three competing narratives for a cosmic origin story. Yet whichever path the universe took, the story doesn't end with the seed. Because even a heavy seed 100,000 times the mass of the Sun is not a billion solar mass monster. The second and perhaps even greater challenge remained the feast. To grow by a factor of 10,000 in just a few 100 million years, this black hole had to consume matter at a rate that beggars belief. It had to be fed by a relentless high-pressure fire hose of cold, dense gas, a river of cosmic fuel flowing directly into the galactic core without interruption. Every black hole, however large, is bound by a fundamental principle known as the Eddington limit. It's a cosmic balancing act. As gas spirals into a black hole, it forms a brilliant superheated accretion disk. This disk shines with ferocious intensity, blasting radiation out into space. This outward torrent of light exerts pressure on the inflowing gas, acting as a powerful brake that can halt the accretion process. The Eddington limit is the theoretical maximum rate at which a black hole can feed before the light from its own meal becomes so powerful it blows the remaining food away. For decades we believed this was the ultimate speed limit on black hole growth. But for the ancient Titan, we had discovered it wasn't fast enough. To reach its observed mass in the allotted time, this black hole had to be feeding consistently, at, or even far beyond its Eddington limit for its entire life. This concept, known as super Eddington accretion, was once a fringe theory. Now it was a necessity. It would require a special kind of environment, a cosmic buffet of epic proportions. The host galaxy itself must have been a reservoir of unimaginable quantities of cold gas, a deep gravitational well that could channel this fuel inward. We are talking about vast cold streams of hydrogen flowing along the filaments of the cosmic web, like cosmic rivers, and plunging directly into the heart of the galaxy, bypassing the disruptive shockwaves of star formation. This presents us with a profound paradox. The early universe was a violent place. The very star formation that would build the galaxy and provide some of the gas also creates chaos. Supernovae from the first stars would have exploded like cosmic bombs, heating and expelling gas from the galaxy's core, starving the nascent black hole. To sustain this level of extreme feeding, the host galaxy needed to be a haven, a place where these cold streams could flow unimpeded. It needed to be a place of immense supply, but also unnatural calm, a quiet harbour in the midst of a cosmic hurricane. Finding a physical mechanism that allows a black hole to gorge itself so far beyond its theoretical limit, while its host galaxy simultaneously protects its food supply from its own self-destructive star-forming tendencies, is one of the greatest challenges in modern astrophysics. We had the culprit, a supermassive black hole in the cosmic dawn. We had our list of suspects for its origin, the immaculate conception of direct collapse, the gang violence of runaway mergers, or the ghostly inheritance of a primordial seed. But we were missing the crime scene. We couldn't yet see the unique extreme galactic environment that must have served as the nursery for this impossible object. The discovery had not provided an answer. It had shattered our questions into 1,000 more, each one deeper and more complex than the last. And it sent us back to our telescopes to peer even deeper into the dawn, no longer just searching for the first lights, but for the immense shadows they must have been born from. We were now hunting for the cradles of giants. So there it hangs in the abyss of cosmic dawn, a behemoth of impossible gravity. But its mere existence, the sheer shock of its mass and its age, is not the most profound chapter of this story. The true revelation, the discovery that is now forcing us to rewrite the very first chronicles of the universe, lies not in what this object is, but in what it was furiously, relentlessly and creatively doing. We had long envisioned the first galaxies as fragile, chaotic islands slowly coalescing from the primordial mists, with their central black holes growing almost as an afterthought, a passive consequence of accumulating matter at the centre. This ancient titan, however, tells a different story. It suggests the relationship was never passive. It was a violent, symbiotic and fundamentally architectural partnership from the very beginning. This was not a cosmic sinkhole waiting to be fed. It was the engine, the furnace and the sculptor of its own nascent galactic kingdom. Imagine it not as a point of no return, but as the gravitational heart of its stellar empire, a cosmic pacemaker, setting the rhythm of birth and death for billions of stars. Even before it ignited into a full-blown quasar, its immense gravity served as an anchor, a central point of order in the swirling chaos of the early cosmos. It was a well so deep that it dictated the flow of all surrounding matter, pulling in vast cold filaments of hydrogen gas that webbed the young universe. These were the galactic supply lines, the rivers of creation stuff, and this black hole was the confluence, the nexus, where the first true metropolis of stars would be built. It was a gravitational gyroscope stabilizing the spinning disk of its infant galaxy, preventing it from simply flying apart into a disordered spray of stars. This single object, a flaw in space-time itself, was providing the fundamental blueprint, the scaffolding upon which an entire galaxy, our cosmic ancestor, would be constructed. The old sequence of galaxy first, black hole second has been irrevocably shattered. Here, in the deepest exposures of our most powerful telescopes, we are witnessing evidence that perhaps the black hole came first, or at the very least that they grew together in a furious, inseparable embrace. They were not just inhabitants of their galaxies, they were the architects. But gravity, even on this immense scale, is a quiet, persuasive force. The true architectural work, the aggressive sculpting of a galaxy's destiny, required a far more violent set of tools, and for that we must look to the light. As those cosmic rivers of hydrogen gas spiraled inwards, they did not fall silently into the abyss. Instead, they formed an accretion disk, a maelstrom of matter wider than our solar system, a churning vortex of friction and fury heated to millions of degrees. This disk became the single most luminous object for light years in every direction, a celestial blowtorch that blazed with the light of 1 trillion suns. It was this terrifying, brilliant structure that transformed the black hole from a passive gravitational anchor into a dynamic cosmic engine. This is the heart of a phenomenon we call black hole feedback, a concept that has fundamentally altered our understanding of the universe's evolution. The term sounds gentle, almost technical, but the reality is one of unimaginable violence. Feedback is the mechanism by which the black hole talks back to its galaxy, regulating its growth with brutal, unflinching efficiency. From the inferno of the accretion disk, two titanic forces are unleashed. First, an immense wave of radiation. A tsunami of high-energy photons pours out across the galaxy, superheating the surrounding gas clouds. This alone is enough to disrupt the delicate process of star formation, warming the cold, dense nurseries where stars would otherwise be born and preventing them from collapsing under their own weight. But this is only the beginning. The second force is even more dramatic. A wind, a galactic-scale hurricane, is driven off the surface of the disk. This is not a wind of air, but a gale of charged particles, protons and electrons blasted outwards at a significant fraction of the speed of light. This outflow, this ceaseless storm, sweeps through the stellar disk of the young galaxy like a colossal broom, literally clearing out the raw materials for new stars. And in the most extreme cases, when the black hole is feeding at its most voracious rate, it can launch something even more spectacular: twin relativistic jets. These are tightly focused columns of plasma, magnetically confined beams of matter and energy screaming away from the black hole's poles at over 99% the speed of light. They're cosmic lances that can punch entirely out of the galaxy, travelling for hundreds of thousands of light years into the empty space beyond, heating and disrupting the intergalactic medium itself. This feedback loop, this system of galactic self-regulation, creates a breathtakingly intricate dance. Think of it as the universe's primary immune system, preventing the cancer of runaway star formation. A young galaxy rich in cold gas begins to form stars at a furious rate. This same gas also funnels down to the central black hole, feeding it, causing it to grow. As the black hole swells, its accretion disk ignites into a quasar, and its powerful feedback, the radiation, the winds, the jets, turns on. This energy blasts through the galaxy, heating and expelling the gas. Star formation, starved of its cold fuel, grinds to a halt. The galaxy's growth spurt is forcibly suppressed. But in doing so, the black hole also cuts off its own food supply. The quasar, now starved, begins to dim. The feedback weakens. The winds die down. Without this constant pressure, gravity once again takes hold. Gas that was pushed away begins to cool and rain back down onto the galaxy's disk. Star nurseries can form again, and the cycle of creation begins anew. It is a cosmic balancing act, a rhythm of feast and famine, of growth and suppression played out over millions and millions of years. And this object, this ancient behemoth from 400 million years after the Big Bang, shows us that this dance is not a recent development. It is a fundamental process written into the laws of the cosmos from the very first dawn. The tight correlation we see in the modern universe between a galaxy's mass and the mass of its central black hole is no accident. It's the result of this eons-long co-evolutionary partnership, a relationship forged in fire at the very beginning of time, a relationship we are only now beginning to comprehend. This realization that black holes are not destroyers but regulators is already a revolution in itself. But their role in the grand cosmic story we are now learning was even more critical. It was a role that affected not just their own host galaxies, but the structure and fate of the entire universe. To understand it, you have to remember what that early cosmos was like. Following the initial fireball of the Big Bang, the universe cooled. Protons captured electrons, forming neutral hydrogen atoms, and with that the universe became opaque. It entered a period known to us as the Cosmic Dark Ages. A star might ignite here, a galaxy might flicker there, but their light could not travel far before it was absorbed by the thick, pervasive fog of neutral hydrogen that filled all of space. For hundreds of millions of years, the universe was a murky primordial soup, its true grandeur shrouded from view. The first stars and galaxies began to produce ultraviolet light, which could ionize the hydrogen atoms, stripping away their electrons and carve out small, localized bubbles of transparent space around them. But these early stars were not powerful enough. Their individual bubbles were not sufficient to clear the fog on a cosmic scale. The universe needed a much bigger, much more powerful source of ionizing radiation. It needed a network of celestial lighthouses blazing with unimaginable intensity to burn away the fog once and for all. And that is the final climactic role played by this ancient black hole and its countless siblings. Each one of these early supermassive black holes, when actively feeding, became a quasar an engine of light outshining its entire host galaxy by orders of magnitude. They were the most powerful beacons in the young cosmos, and they unleashed a torrent of high-energy ultraviolet photons and X-rays. This radiation was the scythe that cut through the cosmic dark. Around each quasar, a vast bubble of transparency grew far larger and more rapidly than anything a mere galaxy of stars could produce. And as more and more of these black hole engines ignited across the universe, their individual bubbles of ionized plasma began to expand and overlap. They merged, creating ever larger voids in the cosmic fog. A percolation of light, a phase transition for the entire universe was underway. This was the epoch of rionization, the most significant transformation of the universe since the Big Bang itself. And it was driven in large part by the collective fury of these very first black holes. They were the architects of light, the agents of clarity. They worked in concert to systematically dismantle the hydrogen fog to tear the opaque veil that had shrouded the cosmos for an eternity. When their work was done, the universe was left transparent. Light from the most distant objects could now travel unimpeded across billions of light years, eventually reaching our telescopes and allowing us to piece together this very history. Without the violent feedback of these cosmic monsters, without their ravenous appetites and the brilliant blaze of their accretion disks, the universe might have remained a dim, murky place for much longer. The formation of the large-scale structures we see today, the great clusters and superclusters of galaxies, would have been delayed, or perhaps would have proceeded in a completely different way. They did not just build their own homes, they cleared the entire cosmic neighbourhood, terraforming the universe on a scale we can barely imagine, making it hospitable for the complex web of structure of galaxies, of stars, of planets, and ultimately of us. The universe was now transparent, its grand architecture finally revealed for all to see. But the architects themselves, having reshaped the cosmos in their own image, would eventually retreat back into the shadows of their galactic cores, leaving behind a universe forever changed by their passage, and a profound, humbling new set of questions for us to answer. And so, our journey across 13 billion years comes full circle. We return to that single defiant point of light, the ghost of a quasar that ignited the imagination and shattered our cosmic timeline. It began as a smudge in an image, a statistical anomaly gleaned from the deepest portrait of the universe ever taken. Yet within that faint red-shifted glow, we discovered a monster, a supermassive black hole, 1 billion times the mass of our Sun, thriving in an era where we thought only cosmic toddlers could exist. This wasn't just another discovery. It was a temporal paradox, an object whose very presence felt like a violation of cosmic law. The universe, it seemed, had a secret history, and the James Webb Space Telescope had just handed us the first page. We have walked you through the frantic calculations, the late nights spent by astronomers staring at data that refused to make sense. We have explored the established theories, the elegant models of gradual orderly growth that had served us so well for decades. These were the pillars of our understanding, predicting a slow, methodical process where black holes patiently feed over billions of years, growing from the stellar embers of the first giant stars. But this ancient behemoth refused to conform. It had achieved its impossible mass in a mere blink of cosmic time, growing at a rate that seemed to defy the fundamental physics of accretion. It was as if we had discovered a towering skyscraper in a fossil bed, from an age before complex life had even evolved. The timeline was broken and the rules had to be rewritten. This quest forced us to confront the deepest questions about origins. If not from a simple stellar seed, then from where we descended into the theoretical wilderness of the cosmic dawn, exploring the radical idea of direct collapse, black holes, primordial clouds of hydrogen and helium so vast and pure that they could sidestep the entire cycle of star formation. Imagine a cosmic deluge, a cloud collapsing under its own immense gravity, not into a brilliant star, but directly into the utter darkness of a singularity. These were the hypothetical heavy seeds, objects, born not in the thousands, but in the hundreds of thousands of solar masses, giving them the crucial head start they needed. For years they were a fringe concept, a clever solution on a blackboard. But the light from this one quasar transformed them from a possibility into a compelling frontline necessity. It provided the first piece of powerful circumstantial evidence that the universe's nursery for black holes was far more exotic, far more violent, and far more efficient than we ever dared to believe. The implications of this ripple outwards touching everything we thought we knew about the genesis of structure in the cosmos. For decades, we have debated the profound chicken and egg problem which came first, the supermassive black hole or the galaxy that surrounds it. We had long observed a strange and beautiful symmetry in the modern universe, a lockstep relationship between the mass of a galaxy's central bulge and the mass of the black hole slumbering at its heart. This cosmic scaling law suggested a deep symbiotic connection, a shared history of growth and evolution. But we could never be sure which was the conductor and which was the orchestra. This ancient quasar, however, offers a stunning new perspective. Here in this fledgling proto-galaxy, the black hole appears almost comically oversized, a gravitational titan completely out of proportion to its host. It suggests a universe where the black holes came first. It paints a picture of a top-down model of cosmic creation, where these gravitational anchors were the first objects to form acting as the seeds around which the first galaxies would crystallize. They were not passive residents. They were the architects, the engineers. Their immense gravity gathered the primordial gas, while their ferocious output, the jets and winds from their accretion disks, acted as a cosmic regulatory system. This outflow of energy, a celestial blowtorch of unimaginable power, could blast through the galaxy, clearing out gas and quenching star formation, shaping the very size, structure and destiny of its galactic home. We are no longer looking at a black hole. In a galaxy. We may be looking at the very engine that built a galaxy. This single object challenges us to see these singularities not as cosmic vultures, but as creators, as the gravitational hearts that pumped the first galaxies into existence, establishing a blueprint for cosmic structure that would echo through all of subsequent time. Its influence extends even further into the very nature of the universe itself. We journeyed back to the epoch of reionization, that mysterious era when the cosmos emerged from a long dark age. For hundreds of millions of years after the Big Bang, the universe was shrouded in a thick neutral fog of hydrogen gas, opaque to the kind of light that would one day form stars and galaxies. Something had to burn that fog away. For a long time, the prime suspects were the collective glow of the first small galaxies, a slow, creeping dawn of a billion tiny lights. But the sheer power of this single ancient quasar presents another culprit. These objects and others like it were not tiny flames. They were cosmic lighthouses blasting out torrents of high-energy ultraviolet radiation. A population of such early supermassive black holes could have acted as the primary catalysts of reionization, carving out vast bubbles of transparency in the primordial gloom with astonishing speed and efficiency. They didn't just illuminate their own galaxies, they helped make the entire universe visible, paving the way for the grand star-filled cosmos we inhabit today. Our view of this pivotal moment in cosmic history has been forever sharpened, and the supermassive black hole has been recast as a potential hero in the story. So where does this revolution leave us now? We stand at a precipice staring into a newly revealed abyss of ignorance, and it is a thrilling, exhilarating place to be. Every great discovery in science is not an endpoint but a doorway. It answers one question only to unlock a dozen more, each more profound than the last. How common are these ancient giants? Was this a one-in-a-trillion cosmic freak, or are we about to find an entire population of these monsters lurking in the shadows of the cosmic dawn? What were the exact mechanisms that allowed them to gorge on matter so ferociously? And can we ever hope to witness the birth of such an object directly? For all its power, the James Webb Space Telescope can only show us the light from the quasar, the incandescent scream of matter being consumed. It cannot show us the black hole itself. It cannot show us the moment of its creation. For that, we need to perceive the universe in a completely different way. We need to move beyond sight, beyond the electromagnetic spectrum. We need to learn how to listen. We need to listen to the sound of space-time itself. For a century, we have known that gravity is not a force but a curvature in the fabric of the universe. Massive objects warp this fabric, and when they accelerate, they create ripples, infinitesimal waves of gravity that propagate outwards at the speed of light. These gravitational waves are the whispers of cosmic events, the echoes of the universe's most violent and secretive processes. They are a ghostly messenger passing through planets, stars, and entire galaxies as if they were nothing, carrying an uncorrupted story of their origin. We have already begun to hear the chirps of stellar mass black holes colliding thanks to ground-based observatories. But to hear the symphony of the supermassive, to tune into the low-frequency gravitational hum of the early universe, we must build an observatory of truly cosmic proportions. We must build it in space. This is the dream of LISA, the Laser Interferometer Space Antenna. It is a mission of breathtaking ambition, an endeavour that redefines the very concept of a telescope. LISA will not be a single spacecraft, but a celestial triangle, a constellation of 3 satellites orbiting the Sun in Earth's wake. These 3 craft will fly in a precise formation separated from each other by 2.5 million kilometres of distance, more than 6 times that between the Earth and the Moon. They will be connected by nothing but pure laser light beams fired back and forth, constantly measuring their separation with a precision so extreme it can detect a change smaller than the width of an atom. This vast triangular web is the instrument. The entire formation is designed to feel the gentle squeeze and stretch of space-time as a primordial gravitational wave washes over our solar system. LISA will be a gravitational gyroscope, a cosmic seismometer, feeling the faintest tremors from the dawn of creation. With LISA, we will finally have the tool we need to directly witness the events that forge the universe we see today. It will hear the thunderous merger of the first supermassive black holes, the very process that could have assembled the ancient giant we have been studying. We will no longer have to infer their existence from the light of their victims. We will hear the crescendo of their gravitational embrace, the final violent ringdown, as 2 singularities become one. The data will be so rich we can determine their masses, their spins, their distance, and their place in cosmic history. It will be the fossil record we have been searching for, written not in stone but in space-time. LISA will open a completely new window onto the universe, transforming our understanding of gravity in the process. We will hear the continuous overlapping gravitational chorus from millions of binary star systems within our own Milky Way, a background hum against which more dramatic events will play out. We may even hear the whispers from the universe's first second, the gravitational echoes of cosmic inflation itself. It is a generational quest to give humanity a new sense, the ability to hear the silent gravitational symphony that has been playing across the cosmos unheard for 13.8 billion years. And LISA will not work alone. Here on Earth, a new generation of behemoths is rising. The extremely large telescope, the 30-metre telescope, the giant Magellan telescope, these are not mere upgrades. They are categorical leaps in power and perception. Their enormous mirrors, dozens of meters across, will gather light from the faintest, most distant objects imaginable, working in concert with Webb to dissect the chemical composition of the very first galaxies, to crystallize around these black hole seeds. They will probe the tenuous cosmic web, the vast filaments of gas that fed these hungry giants, tracing the flow of matter from the largest scales down to the accretion disks themselves. Together, this multi-messenger, multi-wavelength fleet of observatories will conduct a coordinated assault on the mysteries of the cosmic dawn. Webb will find the targets, the ground-based giants will analyse their chemistry, and LISA will listen for their violent origins. We are on the cusp of a golden age of cosmology, where our picture of the universe's first billion years will transform from a few scattered snapshots into a rich, detailed feature-length film. Our journey began with a single photon, a particle of light that had travelled for over 13 billion years, carrying a story of impossible creation from the edge of time. That photon, captured by a mirror of gold and beryllium a million miles from Earth, set in motion a chain of inquiry that has shaken the foundations of astrophysics. It has forced us to abandon comfortable ideas and embrace radical new ones. It has shown us that the early universe was not a slow, gentle, or predictable place. It was a chaotic realm of unimaginable violence and breathtaking speed, a cosmic crucible where giants were forged in fire and gravity. The discovery of this ancient black hole is a profound testament to the power of human curiosity, the relentless drive to ask why. It reminds us that the universe is always more clever, more complex and more astonishing than our theories predict. We build our models, we draw our lines, we write our equations, and then from the deepest darkness, a single point of light appears and teaches us that the story is grander than we ever knew. The quest is far from over. In fact, it has just begun. The light from this object is a message from our own ultimate past, a glimpse into the ancestral chaos, from which our galaxy, our sun, and we ourselves are the distant descendants. As we look to the future, to new telescopes that will see further, and new observatories that will hear the unheard, we do so with a renewed sense of wonder. We know now that the darkness of primordial space is not empty. It is filled with the ghosts of giants waiting to be discovered, and in searching for them, we're doing more than just mapping the cosmos. We're piecing together the first, most violent and most important chapter of our own universal origin story. The answers are out there, written in ancient light and gravitational echoes, waiting for us to see, to listen and to understand. The dawn is breaking, and we are finally learning how to watch.